variation of parameters. So let's say that we had a second order differential equation in the form a sub 2 of x times y double prime plus a sub 1 of x times y prime plus a sub o of x times y equals g of x. The first thing that we want to do is we would want to put this in standard form. So whatever is in front of your y double prime, just divide everything by that. And to put this in standard form, once you divide everything by whatever's in front of y double prime, you'll have y double prime plus whatever's in front of your y prime, that's going to be your p of x, plus whatever's in front of your y, that's your q of x, and then whatever's on the right side of your equation, that's your f of x. Alright, so the way that we solve this is by first solving for the complementary solution. Okay? And then whenever we solve for the complementary solution, we will have two solutions if it's a second order differential equation. And we'll need to make sure that those two solutions are linearly independent. We will need to make sure that their Wronskian is not equal to 0. Alright. After that, then we're going to have to calculate some other things. Now this is kind of, I guess you could say in a way, this kind of reminds me of Kramer's rule in just a small way, because we have to get part of our other solutions, and our other solutions are going to come from these formulas. U sub 1 prime is going to be equal to something called W sub 1 divided by W, where W sub 1 is equal to the determinant, the 2 by 2 determinant, 0 f of x y sub 2 y sub 2 prime, where y sub 2 is one of your complementary solutions. Now this W here, this is the Wronskian of your two complementary solutions. So this W sub 1 is like Wronskian sub 1, I guess you could think of it, but it may be easier for you just to think of it as W sub 1 is going to be whatever you get out from this determinant. And then from that we calculate U sub 1 prime by saying whatever that answer is divided by the Wronskian that we've already figured out when we were doing our complementary solutions to make sure that they are linearly independent. Okay? And then our U sub 2 prime, and we use these to get our other answers. So our U sub 2 prime is going to be equal to Wronskian sub 2 divided by the Wronskian. And Wronskian sub 2, or W sub 2, is equal to the 2 by 2 determinant, y sub 1 prime, 0 f of x. Okay. in a way, it's kind of like Kramer's rule. You know how you have to replace things in the determinant and work it out, and then you have to divide by the answer you get from this other determinant. So if you remember Kramer's rule, it's kind of like that, but we're doing Wronskians here instead of just values from systems of equations or from matrices. Okay, so let me show you how to do this. Make a little more sense, hopefully. And I'll show you how to use this u sub 1 prime and u sub 2 prime to get other answers. So let's say that we wanted to solve y double prime minus 4y prime plus 4y equals x plus 1 times e to the 2x. So the first thing that we would want to do is figure out the complementary solutions. The complementary solutions come from the left side of the differential equation. And so that would be m squared minus 4m plus 4 equals 0. So that's the auxiliary equation. And from that, if we were to factor, we could solve for m pretty easily. That's just going to be m minus 2 times m minus 2. And so we get m sub 1 equals 2 and m sub 2 equals 2. So that's a repeated. So y sub c is equal to c sub 1 times e to the 2x plus c sub 2. Now, do you remember how to get this answer? If it's repeated, you have to put a what? X. So x e to the 2x. All right, so that's our complementary solution. Now, from that, we get y sub 1 and y sub 2. Y sub 1 is going to be just e to the 2x, and y sub 2 is going to be x e to the 2x. Now we need to calculate the Wronskian of those because we have to use this to help us figure out other solutions. So the Wronskian of e to the 2x, x e to the 2x is equal to the 2 by 2 determinant. You say e to the 2x, x e to the 2x. To make this square, you would have to take one derivative. So this is 2e to the 2x. And then for this derivative, you have to use the product rule. So it would be 2x e to the 2x plus e to the 2x. Now, work out the determinant. Multiply this diagonal, and you get 2x e to the 4x plus e to the 4x. So it's this diagonal minus this diagonal, the product of this diagonal. So that's going to be 2x e to the 4x. So you can actually see that these two like terms cancel out and leave you with e to the 4x. So that's what our Wronskian of two of our solutions is equal to. Alright, since the coefficient of y double prime is already 1, there's nothing that we have to do. If the coefficient wasn't 1 in front of y double prime, at this point, this is when you would need to make the coefficient equal to 1. Okay? But it's already 1, so what is our f of x equal to here? F of x is simply equal to the right side of the differential equation. So f of x is equal to x plus 1 times e to the 2x. That's just the right side of the differential equation. That could change if there would have been something different in front of y double prime. All right. So now that we know what f of x is equal to, we need to follow our formulas for w sub 1, we need to find that, and w sub 2. Then we're going to go back and we'll be able to solve for u sub 1 prime and u sub 2 prime. Alright, so I'm going to solve for w sub 1. With w sub 1, you need to remember that your first column is equal to, always equal to, 0 and then f of x, whatever your function is. So that's going to be x plus 1 times e to the 2x. Now, your second column is always equal to your second answer, your y sub 2 that we got. That was x e to the 2x. And then you have to take the derivative of that to put beneath it. Okay, so that would be, we've already done that once, 2x e to the 2x plus e to the 2x. Now, this determinant is pretty easy to work out because when you multiply this diagonal, you get 0. Minus, now you have to multiply this diagonal. You can write it a couple of different ways. It doesn't matter how you write it. But all I'm going to do is I'm going to write this. I'm going to say e to the 2x times this and write that in front of the parentheses. Right. So it's x e to the 4x times x plus 1. And so that's just equal to negative x e to the 4x times x plus 1. You can multiply that out, but I would suggest leaving it in factored form like that. So that's our Wronskian sub 1. Let's go ahead and find our Wronskian sub 2, or our w sub 2. So just like how you have to change things up with Cramer's rule, you don't always, I think with Cramer's rule, you replace a row, the variable that you're trying to solve for, by like what all your equations are equal to or something like that. It's very similar. W sub 2, the second column needs to start with a 0, and then underneath that you put the f of x. So that's going to be x plus 1 times e to the 2x. Now the first column with w sub 2 is y sub 1 and its derivative. Y sub 1 was e to the 2x, and then its derivative is 2e to the 2x. Okay, so if we work out this determinant, multiply this diagonal, we get e to the 4x times x plus 1 minus, multiply the other diagonal and you get 0. Alright, so that's e to the 4x times x plus 1. Now, we need to calculate our u sub 1 prime, which is going to be w sub 1 divided by w. We need to figure out what that is, and we want to figure out what u sub 2 prime is equal to. That's w sub 2 divided by w. We've already solved for w sub 1, w sub 2, and w. Alright, so w sub 1 was negative x e to the 4x times x plus 1. The Wronskian, w, was equal to e to the 4x. So more than likely here there's going to be something that cancels out. You see here it will be those two terms, and that leaves you with negative x times x plus 1, or negative x squared minus x, if you distribute the negative x. Okay, that's our u sub 1 prime. We're going to have to use that in just a minute. Alright, our u sub 2 prime is equal to, see, Wronskian sub 2 was e to the 4x times x plus 1 divided by the Wronskian was e to the 4x. So you can see what cancels out, and you're just left with x plus 1. So you can see the u sub 1 prime and the u sub 2 prime simplified down to something that wasn't very complicated. Okay? And so from u sub 1 prime and u sub 2 prime, we can integrate those and get u sub 1 and u sub 2. So we have what u sub 1 prime is equal to. So u sub 1 is going to be the integral of u sub 1 prime, right? Which is going to be, integrate these two terms. You get negative x cubed over 3 minus x squared over 2. U sub 2 is going to be the integral of u sub 2 prime. So that's going to be x squared over 2 plus 1. No, plus x. Sorry. All right. Now, our y sub p is going to be equal to u sub 1 times y sub 1 plus u sub 2 times y sub 2. All of those, the u sub 1 and y sub 1, those could be written as u sub 1 of x, y sub 1 of x, u sub 2 of x, y sub 2 of x. They all mean the same thing. Alright, that's how we get our particular solution. So for this problem, y sub p is going to be equal to, we have negative x cubed over 3 minus x squared over 2 times our y sub 1. You look back, our y sub 1 was e to the 2x. Plus u sub 2 was x squared over 2 plus x, and y sub 2 was x e to the 2x. So once you write down that product of u sub 1 y sub 1 and u sub 2 y sub 2, you need to multiply it out and see if you have any like terms. So that's going to be negative 1/3 x cubed e to the 2x minus 1/2 x squared e to the 2x plus, this is going to be 1/2 x cubed e to the 2x, right, because we have an x on the outside, and then that's going to be plus x squared e to the 2x. And now you can see we do have like terms. This term and this term are like terms, and this term and this term are like terms. So let's see, for the cube term, we have negative 1/3 and positive 1/2. So if you make those sixth, that's 3/6 minus 2/6. So we have 1/6 x to the 3rd e to the 2x. And then we have a positive 1x squared e to the 2x and a negative 1/2 x squared e to the 2x. So negative 1/2 and positive 1, put those together, you get positive 1/2. So that's our y sub p. Now remember, our solution y is equal to y sub c plus y sub p. So our solution would be c sub 1 e to the 2x plus c sub 2 x e to the 2x plus 1/6 x cubed e to the 2x plus 1/2 x squared e to the 2x. So looking back at the same problem, if we find the complementary solution, we have y sub c equals c sub 1 e to the 2x plus c sub 2 x e to the 2x. We get that from the auxiliary equation. Now, once you have that answer, whatever you have after c sub 1, that's going to be your y sub 1. Whatever you have after c sub 2, that's going to be your y sub 2. You find the Wronskian of those two answers. So we found the Wronskian, we got e to the 4x. We're going to use that to help us figure out our complementary, our trial particular solutions. We have to then make sure that we are in standard form. So make sure you have y double prime with a 1 in front. All right, and then if you don't, just divide everything by whatever number is in front there. Okay, and see how it changes the right side of the equation. Whatever your right side of the equation is after you make that y double prime, if you have to do that, that is your f of x. Now, to find Wronskian sub 1, that's going to be the first column is 0 and then f of x. The second column is y sub 2 and y sub 2 prime. All right, that's the column. All right, figure that out. We figured it out. Then go on to Wronskian sub 2. Wronskian sub 2, the second column starts with a 0. And then under that we have f of x. The first column is y sub 1 and y sub 1 prime. Calculate that. All right, so we figured out the Wronskian. We figured out w sub 1 and w sub 2. Now the two things that we need to solve for, u sub 1 prime and u sub 2 prime, are equal to Wronskian sub 1 divided by the Wronskian, Wronskian sub 2 divided by the Wronskian. You figure those two answers out. Some stuff is going to cancel out. And then we integrate each one of these and get u sub 1 and u sub 2. Once you find u sub 1 and u sub 2, your triparticular solution, or y sub p, is equal to u sub 1 times y sub 1 plus u sub 2 times y sub 2. Multiply everything out, combine like terms, and that's your y sub p. That's your particular solution. All right. Your solution is equal to the sum of your complementary solution plus your particular solution. So there's our answer right there. All right, let me work through another one for you. Let's say we had y double prime plus y equals secant theta times tangent theta. All right, so the first thing we need to do is write down figure out our complementary solution. We get that from our auxiliary equation. So we would have m squared plus 1. We don't have a y prime term, so there's no just m to the first term. We set that equal to 0. So we'd have m squared equals negative 1. So m is equal to plus or minus I. Right? Take the square root of both sides, you get plus or minus I. Remember the formula we have to use when we have an imaginary or complex number here. It's alpha plus or minus beta I. All right, and the formula is e to the alpha x times c sub 1 cosine of beta x plus c sub 2 sine of beta x. All right, our alpha is equal to 0, so we're not going to have an e to the 0 is 1, so we don't have that e term on the outside. We do have a 1 for our beta, so y sub c is equal to c sub 1 cosine of 1x plus c sub 2 sine of 1x. Alright, so we have our complementary solution. Now we look back at our differential equation and we see, is it in standard form? And this one is also in standard form. Alright, so there's nothing to divide anywhere, and our f of x is going to be equal to secant theta tangent theta. Now, before we can proceed, we need to figure out our y sub 1 and our y sub 2 that we're going to use in all of our Wronskians that we have to find. So y sub 1 is going to be cosine of x, and y sub 2 is going to be sine of x. So the Wronskian of cosine x sine x, that's going to be the 2 by 2 determinant. First we write down cosine x and sine x, then underneath those we write their derivatives. So that's going to be negative sine x, and the derivative of sine is cosine x. Now let's evaluate this Wronskian. So let's evaluate this 2 by 2 determinant. So cosine times cosine is cosine squared x, then minus negative sine times sine is negative sine squared x. Well, if I have minus negative sine squared x, that's going to be cosine squared x plus sine squared x. We all remember from our Pythagorean identities that sine squared x plus cosine squared x is equal to what? 1. So that's going to make this problem a little bit easier, because Wronskian of our y sub 1 and y sub 2 is just equal to 1. Alright. Now let's figure out the w sub 1. I call that Wronskian sub 1. That may not be the right terminology, but it just kind of makes sense if I do. So I have to remember that with Wronskian sub 1, my first column starts with a 0. You can make that association. Wronskian sub 1 first column starts with a 0. Underneath that you want to put your f of x, which on this problem for us was secant theta tangent theta. And then in the Wronskian sub 1 you put y sub 2 and its derivative. Y sub 2 is sine x. Derivative of sine x is cosine x. So let's evaluate this 2 by 2 determinant. 0 times cosine is 0 minus sine times secant times tangent. Anytime I have a long string of trig functions like this, if I want to see if I can simplify those, you may just want to make them all sine and cosine and see if anything cancels out. If it doesn't, so be it. We'll leave it like it is. But a lot of times when you write this all in terms of sine and cosine, things cancel out. So it's going to be negative sine x times 1 over cosine x. I know I put a theta and an x, but just make them all x. I don't know why I put a theta there. You can make all these x. You can make them all theta. It doesn't matter. Alright, so that's 1 over cosine x. Then that's going to be sine x over cosine x. So you can see, do any of them simplify? No, they don't cancel out. However, if you multiplied straight across, you'll have negative sine squared x over cosine squared x. And you all know that sine squared x over cosine squared x is tangent squared x, right? So our Wronskian sub 1 is equal to negative tangent squared x. Okay, let's see what Wronskian sub 2 is equal to. So my W sub 2, I'll call it Wronskian sub 2, is equal to the 2 by 2 determinant. Sub 2, I'll start the second column off with a 0, and then underneath that I put my f of x, secant x, tangent x. My first column is my y sub 1, which was cosine of x, and then underneath that its derivative, negative sine of x. So let's evaluate this determinant. So that's going to be cosine x times secant x times tangent x minus 0. Anytime you multiply two reciprocal trig functions together, you get 1. Right, because cosine x times secant x, that will be cosine x times 1 over cosine x. So those two cancel out and just leave me with tangent x. Okay. So now that I've calculated my W sub 1 and my W sub 2 and my Wronskian, I can figure out my U sub 1 prime and my U sub 2 prime. My U sub 1 prime is W sub 1 divided by W. Wronskian sub 1 divided by Wronskian. So that's going to be negative tangent squared x divided by 1, which is just negative tangent squared x. My U sub 2 prime is going to be Wronskian sub 2 divided by the Wronskian. And so that's just going to be tangent of x divided by 1, which is just tangent of x. Now we need to figure out, we have U sub 1 prime and U sub 2 prime. We need to figure out what U sub 1 and U sub 2 are equal to. So we have to integrate our U sub 1 prime and our U sub 2 prime. To integrate tangent squared, don't make the calculus 1 or calculus 2 mistake of saying that's tangent or saying that's secant squared. It's not. Right? We all know that you need to apply an identity to that to be able to integrate it. So tangent squared x is equal to secant squared x minus 1. So it's the negative of, let's see, it's going to be the integral of the negative of secant squared x minus 1. Because tangent squared x is secant squared x minus 1. Which is something we can integrate. You can integrate that, right? You can integrate secant squared, that's tangent. So you get negative tangent x, and then the integral of negative 1 is just x. So apply that negative. So it would be the negative of negative x or plus x. So you get negative tangent x plus x. I integrated those and distributed to the negative. Now what's the integral of tangent of x? That's not secant squared. You know, I have students all the time that try to do that. It's not right, right? We know we can only integrate sine and cosine with our derivative rules. Kind of help us out. But all the other 4 trig functions, when you integrate them, they're the natural logs, right? So the integral of tangent of x is negative natural log absolute value cosine of x. All right, so we have solved for U sub 1 and U sub 2. So that means we can figure out our y sub p, our particular solution, because it's equal to u sub 1, y sub 1 plus u sub 2, y sub 2. So our u sub 1, I'm going to reverse these two because x is positive and tangent's negative. So I'm going to write x minus tangent instead of negative tangent plus x. This makes me feel better if I do that. I don't know why. All right, times y sub 1. Y sub 1 was cosine of x. Plus u sub 2, that's negative natural log absolute value cosine x times y sub 2. Our y sub 2 was sine of x. And so it is this term times this whole term, so don't get that mixed up. You can't multiply the cosine and sine together. This is natural log cosine of x. Alright, so that means our particular solution is equal to, we can distribute this, and we want to distribute the cosine because that actually simplifies one of the terms. We have x cosine of x minus, what is cosine of x times tangent of x? Remember, tangent is sine over cosine. So if you multiply that times cosine, that just leaves you with sine. Alright, so we have, this is our, all of this right here is our first part. And then minus, I would write the sine in front, minus sine x times natural log absolute value cosine x. So that's our y sub p. There are no like terms to combine. So y is equal to y sub c plus y sub p is equal to, our complementary solution was c sub 1 cosine of x plus c sub 2 sine of x. Now, look at, I'm gonna write out these others. We have to put plus y sub p. I have x cosine x minus sine x minus sine x times natural log absolute value cosine x. So look at all of those terms. Now, the reason I say look at all of those terms because this term and this term are like terms. C sub 2 in front of sine stands for any constant, which also includes negative 1 because that's negative 1 times sine of x. So what you want to do to write your final answer, since those terms were similar, just write y equals c sub 1 cosine of x. Then to show that I've put those two terms together, I'm going to put plus c sub 3 sine of x. That just shows that these were the same, and I kind of, put them together and made that c sub 3 plus x cosine x minus sine x times natural log absolute value cosine x. Now you may be thinking, why is it x cosine x and c sub 1 cosine x? Why aren't those like terms? Well, because x is a variable and c sub 1 stands for a constant. X could be anything. It doesn't have to be a constant. All right, I have one more problem I want to work for you. So let's solve 4y double prime plus 36y equals cosecant 3x. Now, this is one where there's not a 1 in front of y double prime. while you may think that it does affect the answer for your complementary solution, it doesn't. You can work it out as 4m squared plus 36 equals 0, or you can work it out as m squared plus 9 equals 0. You get the same answer, right? That doesn't really affect the complementary solution. So this would be, let's see, that would be equals negative 36, divide by 4, divide by 4. You get m squared equals negative 9, take the square root, take the square root. You get m equals plus or minus 3i. So alpha plus or minus beta I, ours is going to be 0 plus or minus 3i. So again, our alpha is 0. So y sub c is going to be equal to c sub 1 cosine of 3x plus c sub 2 sine of 3x. I got the 3 from what's in front of the I, that's the beta. All right, now it will matter though whenever we're trying to figure out our Wronskians and our u sub 1 and u sub 2 prime if this isn't a 1 in front. So you can either do it at the beginning of the problem, or you can do it right now. You get the same answers up to this point, okay? But after this, you don't get the same answers if you don't do that. So you need to make sure that you do that at some point. So our f of x is now equal to 1/4 cosecant 3x. All right, so let's figure out our Wronskian. Remember, our Wronskian comes from y sub 1 and y sub 2, which come from the complementary solution. So if I take the Wronskian of cosine 3x sine 3x, that's going to be equal to cosine 3x sine 3x. The derivative of cosine is negative 3 sine 3x. The derivative of sine is 3 cosine 3x. All right, so if you cross multiply, you get 3 cosine squared 3x minus negative 3 sine squared 3x. And so you have minus and negative, so that's plus. If you factor a 3 out, that leaves you with cosine squared 3x plus sine squared 3x. As long as those are the same, that's always equal to 1. So that's 3 times 1, or 3. So our Wronskian is equal to 3. So we need to figure out our Wronskian sub 1 and our Wronskian sub 2. The Wronskian sub 1, we put a 0 in the first column, then we put our function underneath. Second column is y sub 2, so that's sine 3x, and then the derivative of that underneath would be 3 cosine 3x. All right, cross multiply. So I'm going to get 0 minus, I have 1/4 cosecant 3x times sine 3x. Cosecant and sine are reciprocals. So cosecant 3x times sine 3x is equal to 1. Anytime you multiply a trig function times its reciprocal function, you get 1. So that's just going to be equal to negative 1/4. Probably the easiest one we've worked out so far. Our Wronskian sub 2, in our second column we put a 0, and then we put 1/4 cosecant 3x. In our first column we put y sub 1, just cosine 3x. Underneath that you put the derivative, negative 3 sine 3x. Now, work out that 2 by 2 determinant, and you get 1/4 cosecant 3x times cosine 3x minus 0. Now, cosecant cosine. Cosecant is equal to 1 over sine. So that's 1 over sine 3x. So that's equal to 1/4. What's cosine over sine? Cosine divided by sine. Cotangent 3x. All right, so we have solved for the Wronskian, Wronskian sub 1, Wronskian sub 2. So our u sub 1 prime is equal to Wronskian sub 1 divided by the Wronskian. Wronskian sub 1, we got negative 1/4. Divided by the Wronskian, 3. So that's negative 1/12. Wronskian sub 2, u sub 2 prime is Wronskian sub 2 divided by the Wronskian. So we got that as 1/4 cotangent 3x divided by 3. So that's 1/12 cotangent 3x. Now integrate each one of those u's. You get that u sub 1, integrate negative 1/12. What do you get? Negative 1/12 x. Integrate cotangent. What do you get? Do you remember that integral? You do have a u here. So your u is 3x, so your du is 3, so you need to bring out a 1/3. There's already a 1/12 on the outside, so that's going to be 1/36. And then the integral of cotangent is natural log sine. So it's times the natural log absolute value sine 3x. Okay. So we are basically done. All we have left to do is find y sub p. Y sub p is u sub 1, y sub 1 plus u sub 2, y sub 2. So that is negative 1/12 x, and then y sub 1 is equal to cosine 3x. And then plus u sub 2, which is 1/36 natural log absolute value sine 3x times y sub 2. Y sub 2 was sine 3x. So that means that y equals c sub 1 cosine 3x plus c sub 2 sine 3x minus 1/12 x cosine 3x plus 1/36 times the sine of 3x times the natural log absolute value sine of 3x.